Alright, welcome to another video. This is just building on what we learned in your index of refraction lab that you submitted yesterday. So we're going to just start talking about what the index of refraction is and how it relates to what's referred to as Snell's law. So index of refraction is the number that you got when you looked at your angle of incidence versus your angle of refraction. So when you looked at the sine function of that. So it is the ratio of the speed of light in a vacuum. Oops, sorry, no spelling mistake there. In a vacuum to the speed of light in a specific medium. So for your lab, you went from air to glass, or you went air to oil, or air to water. All right, so we'd be looking at the speed of light in the air versus, or compared to the speed of light in the specific medium. So that's really what your index of refraction is. Now, that's shown by this formula, or N equals C over V. All right, where N equals the index of refraction, C equals speed of light in a vacuum, and that is 3.00 times 10 to the 8 meters per second, and then V equals speed of light in a specific medium. Right, so again, we're looking at that ratio. Again, this is the ratio. So this, looking at speed of light over the speed in the medium. Now, what you looked at in your lab was this ratio, which is looking at the same thing, just in a different form. So you looked at N equals the sine of the angle of incidence over the sine over the angle of refraction. So in your lab, you looked at that relationship. It's just that in this particular case, we're looking at angles. Well, the angles reflect the same comparison as the speed of light. So that's why we can use the sine function. This really is looking at Snell's law, which is something that some of the groups you found in your research, that you're looking at Snell's law. So I'm just going to quickly go over what Snell's law is, because it's just a building block of what we looked at in terms of our ratio between the sine of angle of incidence and the sine of angle of refraction. So Snell's law is N I, which is the index of refraction of your incident ray, times, the dots is representing times the sine of your angle of incidence equals the index of refraction times the sine of theta r. Alright, so again, that's refraction. So just to go over that. So this is your index of refraction for when the ray is traveling through your first medium. So in your case, it was air. This is your angle of incidence, right? So remember, that is from your normal to your incident ray. This is your incident or your index of refraction. So this is your second medium, and then this is your angle of refraction, again from your normal to your refracted ray. Now, to show you this on a diagram, again, we would draw our barrier. We are then going to take our incident ray, oops, right, so the incident ray is going to hit the barrier, like that. Remember, we have our normal. Our normal is going straight down. Again, it goes into both mediums. We are then looking at our refracted ray. So to show this equation on a diagram, what we're looking at is our angle of incidence, our angle of refraction. This is one specific medium, so this would be your index of refraction for, say, air. So say that's 1.00, which would be air. You use crown glass, so your index of refraction would be 1.52. So again, this, you're looking at that relationship. So this is the first part of the equation, right? So the index of incident ray, so what medium is traveling through. This is the incident of refraction. Not incident of refraction, sorry. Your angle of incidence, angle of refraction, and then this is your second medium. So let's take a look at a practice question. So let's take a look at example A. So we're going to set this problem up. That's going to be our barrier. We're going to have our incident ray. We will then draw our normal. We are going to be given the following information. So we're going to have our angle of incidence, that's going to be equal to 45 degrees. Our index of refraction for our incident side is going to be 1.0. And our incident of refraction, our index of refraction is going to be 1.33 for our refracted side. We are trying to figure out our angle here. We are trying to figure out our angle of refraction. So we're going to take that information, we're going to plug it into the formula. So remember, the formula is Ni times the sine of our incident, angle of incidence, and of our refracted times the sine of our angle of refraction. So we know that this is 1.00 times the sine of 45 equals 1.33 times the sine of theta r. We're going to rearrange that, so it's going to be the sine of theta r equals 1 times the sine of 45 divided by 1.33. The sine of theta r equals 0.70710678. That's going to go on and on and on, so I'm just putting down those numbers. Again, I'm taking the sines. Remember that from your calculations. Put in your calculator the sine of 45, it's going to give you a decimal, and then you're going to multiply that 1, and then you're going to divide that by 1.33, which is the index of refraction for your refracted ray side. When you get to this point, this is really 0.70710678 divided by the sine. This here is really taking sine to the -1, so you're doing the inverse. So on your calculator, you would do your second function sine and then this decimal, or your calculator may work as writing this decimal and then doing the sine inverse. Either way, you have to do the inverse of sine, so you're doing the opposite of sine, and then that is going to then give you your angle. So you want to give that a try on your calculator because you want to make sure you understand how that function is. So just to review, like this one here, you're just typing in sine 45, that's going to give you a decimal. Here you're going to be given a decimal. To go from a decimal to the angle, you have to do the inverse of sine. So take a look at your calculator. It's probably going to be a second function sine, and then typing your decimal, or typing your decimal, and then second function sine. Give that a try, see if you can get your 32 degrees so you understand what you do when you get into this mathematical situation. Okay, example B. Example B, again, we're going to set this up. We have our barrier. We're going to have our incident ray. We're going to have our normal. Normal's a little bit off, sorry. We're going to then put our information in, so we got angle of incidence, that's going to equal 38 degrees. We're going to now have our angle of refraction. That is going to equal 26 degrees. Our NI is going to equal 1.00. So we're going to try to figure out our refraction. Alright, so this question is focusing on figuring out the refraction, our index of refraction of our second medium here, so this medium, using our angle of incidence, angle of refraction, and our known incident index of refraction for our incident side. So again, we're going to plug in, so we know Ni times sine theta I equals NR times the sine of theta R. Plug that information in, 1.0 times the sine of 38 equals NR, again this is what we're trying to find, times the sine of 26. I'm going to rearrange that, so the index of refraction for the refracted side equals 1.00 times sine of 38 degrees over the sine of 26 degrees. So this is following the same format, right? You're going to plug in your calculator, sine 38, it's going to give you a decimal. Sine of 26, that's going to give you a decimal. You divide all that, and you're going to end up getting 1.4. Now again, there's no units with that. Again, that's just telling you the index, or really the ratio of how much bend is to that light into that second medium. Again, go through this, make sure that when you're doing your example question that you are arriving at the same answer. And then if you're having difficulty with that, that's something that we can focus on in class. But you do want to try that to make sure you understand the difference between just doing sine of 38 versus the inverse sine of 38. So in this case, just doing sine of 38, sine of 26, these are going to both give you decimals, and then you're multiplying by 1. Alright, the last thing I want to talk about is the idea of refraction. And what's called total internal reflection. So, a couple things you probably observed while you're doing your lab last day. So I'm just going to draw these observations out. Is when your angle of incidence hit, again this would be hitting the glass, and you would have had your normal, which would have been at 90 degrees to that. You would have noticed, and through your observations you would have seen that, yep, my angle of refraction is bending either towards the normal or away from the normal. Two situations, and you just want to make note of this. If the angle of refraction is bending towards the normal like this, so by towards the normal, if I drew this straight out, if it just kept on going, there'd be no bend whatsoever. So any bend that's moving towards this direction, so moving this direction, the speed of light is slowing down in the second medium. If we bring this back out, we have a straight line, and the line bends away, so it's bending this way, then the speed of light is faster in the second medium as opposed to the first medium. So again, this is our first medium, this would be our second medium. So again, your normal is the point that is your reference. So if I take this again, bending towards it, right, the second medium is slower. Moving away, second medium is faster, right? And that's something that you would have observed during your lab. All of yours bent towards the normal, which meant that that second medium was actually slowing down light, forcing it to bend towards that normal. The next thing is, or the last thing is, total internal reflection. Now, total internal reflection is something that we're going to observe in a few different situations. So just to give you an idea of what's going to happen is you will have a barrier. You will then have a normal, like you normally would. You're going to have a situation where you have an incident ray coming in. That incident ray hits and is going to create a situation where you have the refracted ray bending away from the normal. So this would have an angle of incidence that is less than an angle of refraction. So we're moving from a slow to a fast medium. So this would be like going from glass to air. This would be like going from the oil to the air, water to the air. So this is a more optically dense medium, or a slow medium, going to a fast. In your last lab, you went the opposite way. You went from fast to slow. So now you're moving from slow to fast. To achieve total internal reflection, this is one of the criteria. You're moving from a slow to fast, so your angle of incidence is actually less than your angle of refraction. So this is your angle of incidence. This is your angle of refraction. Now, if you keep this angle of incidence and you keep moving it out, so you're getting a bigger and bigger angle, what will happen is your refracted ray, so this one here, will disappear and actually just be reflected inside. So to draw that, you would have your barrier. You're going to have your normal. This is going to be slow. This is fast. So we're moving from slow to fast. We're going to have our angle of incidence at a very large angle. So this is your angle of incidence. So that's very large there. When this gets large enough, then you get a situation, instead of your refracted ray coming out here, this disappears. You get no refraction. What you get is total internal reflection. So it actually reflects back into the same medium. So we have our incident ray coming in. Instead of it going this direction, this disappears. You get an internal reflection, or total internal reflection. This is caused by two things, two conditions. So you're going from a slow to fast medium, and also your angle of incidence is at such an angle that your angle of refraction is continually getting greater and greater to a point where it actually just reflects inside the same medium. So no light comes out here. It starts inside the slow medium, doesn't exit, and comes right back in. And that's referred to as total internal reflection. So some things that use total internal reflection are fiber optics. You're going to see triangular prisms, so in uses of like a periscope or a binocular. You're going to see any kind of reflector that's shown on the road. All uses those ideas of internal reflection, which are things that we'll cover in class, things that you will actually start looking up in your textbook and start answering questions about how they work in terms of ray diagrams and so on. So this here is just giving you an introduction to what it is, and it's this information that you will use in class tomorrow to not only answer mathematical questions about the index of refraction, but also taking a look at devices that use total internal reflection in terms of how that works and how we can use that concept in society. All right, so again, that's an overview. You want to take notes on this. You want to come in tomorrow's class and ask questions about anything that's been discussed in this video. And then also you will be working on a beginning of a lens lab tomorrow, where you'll be using the idea of that index refraction again.